Hello guys, welcome on Tesla Adventures. In this video, we'll study the node analysis or nodal analysis in heat transfer. So we have already discussed that what is the analogy between heat transfer through conduction and current electricity in the previous video. And in this video, we are going to apply a special theorem which is nodal analysis in heat transfers for a simple solution of the problem. So in this question it is given, let us take an example. In this question it is given that this rod AB is a rod which has a thermal resistance of 5 Kelvin per watt, and it is joined just at the middle of another identical rod CD. You can see these are the temperatures of these three ends, and we have to find out the heat current flowing in this CD. So let us first of all also find out the temperature at this junction C. So let us name it as T. So we can see that if RAB is equal to R, let's suppose it is R and it is 5, then we can see that this is a combination in which the resistance of AC is R by 2, the resistance of CB is R by 2, and the resistance of C is R. The temperature of this end is 100 degrees Celsius, the temperature of this end is 0 degrees Celsius, and the temperature of this end is 25 degrees Celsius. The temperature of junction is, let's suppose, T. So in nodal analysis, as we have already discussed in current electricity, that we first of all identify the node. So this is the node on which we are going to apply nodal analysis, and we assume that the temperature of this node is highest, and therefore the heat current is flowing away in all three directions, because heat always flows from higher temperature to lower temperature. So as we have assumed the temperature of this end to be highest, therefore we can say that the heat will flow from this end away from this end. So in this direction, and in this direction. Let's suppose that the heat current flowing in this direction is I1, in this direction is I2, and in this direction is I3. So we can say that I1 plus I2 plus I3 will be equal to 0. And therefore we can also say that the heat current is equal to as we compare with current electricity, we can say that I is equal to V by R. So in this case we can say that heat current I1 is equal to delta V, which is the potential difference across these two ends, and it is T minus 100 because we have assumed T to be highest, and divided by R by 2 and I2 will be equal to T minus 25 divided by R, and I3 will be equal to T minus 0 divided by R by 2. And we substitute these values in equation number 1, which is I1 plus I2 plus I3 is 0. So you can see that T minus 100 into 2 by R plus T minus 25 by R plus 2 T minus 0 by R is equal to 0. Let us take R LCM and let us throw it in towards 0, and this equation will simplify as 2T minus 200 plus T minus 25 plus 2T is equal to 0, and 5T will be equal to 225. So the temperature of this junction T will be equal to 225 by 5. So you can see that this is equal to 45. In fact, 45, yes. So this is temperature of this junction. Now we have to find out the heat current in CD. So the heat current in CD was this one, and therefore ICD is equal to I2, and this would be equal to 20 by, this is 45. I am substituting the value of 45 here. So 45 minus 25 is 20 divided by R. R is equal to 5. So the answer is 4 watt. Okay. So this is the value of heat current passing through this CD, and this is the method of nodal analysis to find the junction temperature in the problems of heat transfer through conduction. Now let us move on some other examples. In this problem, you can see that there are 3 rods, each of length A and area of cross section, each of length L and area of cross section A. The thermal conductivity of this rod is 2K, and this one is K, and this one is K by 2. The temperature of the two ends is shown as in the figure, and we have to find out the junction temperatures of the copper and aluminium, which is T1, and the junction temperature of aluminium and brass, which is T2. So let us first of all see that if this resistance is R, so R will be L by 2K. So this will be 2R because its resistance is L by Ka, and this would be 4R. So if I draw the equivalent diagram, you can see that this is R, this is 2R, and this is 4R, and this temperature is T1 and this is T2. Let us suppose that let us suppose that this is node A. Let us name it as A. And let us first of all write down the temperature of this junction, which is 100 degrees Celsius, and this one is 0 degrees Celsius. So first of all, we write down the equation of nodal at node A. So at node A, we can write that T1 minus 100 divided by R plus T1 minus 0 divided by, this is 6R, and that is 0. So you can see that 6T1 minus 600 plus T1 is equal to 0. So 7T1 is equal to 600. So T1 is equal to 600 by 7, which is slightly less than 100. Therefore, the heat will flow in this direction. Now to find out the temperature T2, let us draw a new diagram in which let us write down the node B. So first of all, this is R, 2R and 4R, R, 2R and 4R, and this one was 100 degrees Celsius, and this is node B, and let us suppose that its temperature is T2, and this is 0 degrees Celsius. Okay, so let us again write down the nodal equation at this point. So it is T2 minus 100 divided by this resistance is 3R plus T2 minus 0 by 4R. So taking the LCM, which is equal to 12R, so this is 4T2 minus 400 plus this is 3T2 is equal to 0. So 7T2 is equal to 400, and therefore T2 is equal to 400 by 7. So you can see that the temperature T1 was already given as we have already calculated. It was 600 by 7, and the temperature T2 is 400 by 7. So you can see that this temperature is continuously decreasing as we are moving from the hotter end towards colder end. And therefore, the heat will flow from this side to this side. Thank you. In this question, you can see that there is a wall which has two layers A and B. The layers have equal thickness. So let us suppose that these are two layers, and this layer is A. This layer is A and this layer is B. The thickness of both of these layers is same, T, and the area of cross section of each layer is A. Now we have assumed that area is A and the conductivity of A is twice of that of B. So let us suppose that conductivity of B is K. So its conductivity would be 2K. So under steady state, the temperature difference across the whole wall is 36 degree Celsius. So we have to find out the temperature difference across this layer A. So let us find out the equivalent of these two. So this is RA and this is RB. So you can see that RA will be equal to T upon 2Ka and RB will be equal to T upon Ka. So if this is R, then this is 2R. So let us write down RA as R and RB as 2R. Okay, so you can see that the total potential difference across these two, I am referring as potential difference, but in actual question it is given as temperature difference. So this is 36 degrees Celsius. Okay, so let us suppose that the temperature difference across this one is delta TA and the temperature difference across this one is delta TB. So we can see that delta TA, we have already discussed a formula in potentials, that if the total potential across these series combination of resistances is V, so V1 will be equal to R1V upon R1 plus R2, and similarly V2 will be equal to R2V upon R1 plus R2. So delta TA will be equal to this R into V, which is 36 upon 3R, and delta TB is equal to, this is R2R into 36 upon 3R. So this is equal to 12 and this is equal to 24. So the correct answer is option number B. Now we move on the next question.